All right, so the first two sections on your review, which are also the first two sections on your test, I believe, these are retakes from the last test. This was the whole back side of the last test, and we had some issues specifically here with this question. So when I know it's super tiny on your paper, so you probably can't see it very well. Do your best estimate. But when it says evaluate your function at 4, that's their way of saying x equals 4, what does the y equal? So you would have to follow it over to x equals 4, and then, in case you can't see it on your tiny graph, this is the point when x equals 4, this little minimum down here. So if it was a larger graph, you'd be able to really carefully count and tell me approximately where the y value is. I went with like negative 6.8. I have no idea though, because I'm too old to see that tiny print. So big question mark on this one. I went with negative 6.8. So then for function evaluated at -1, you go over to where x equals -1, find your function. There's your function. And you tell me what y value that is. So again, this is super uber duper tiny. On the test it'll be much larger. You'll be able to tell what the point is. Again, they're estimates, guys. So like I think this one comes out to negative 0.8. But you might think it comes out to negative 0.9 or 0.7 or whatever. Just as long as it's in the ballpark, okay? Some of you missed the boat a little bit on that question last time. Let's do a better job this time. Here you're going to calculate the average rate of change. Remember, average rate of change is really just what? It's really just slope. So if you could figure out what happens when x equals 4 and x equals 2, that just means plug in x equals 4 and plug in x equals 2. And then once you find your y values, then you go find slope. For the sake of time, guys, I'm just going to skip that one. I took a picture of my answer key. No promises that I didn't make any mistakes on it. But you can see my process at least on there if you need to go back and look. Any questions on those two? Those are repeaters. All right, these are extra examples. If we have time, guys, we can come back to that. So, more examples. We'll come back if we need to. This guy, absolute value of x plus 3. Is it a function? Why or why not? So, the reasons why you can tell me if something is a function or not depends on what you were given. Right now, all we have is an algebraic function. Most of you prefer the vertical line test for determining whether it's a function or not. But what do you need in order to use the vertical line test? You need a graph. So if you know this is an absolute value graph shifted up 3, that's great. So it looks something like this. You also have a graphing calculator. Don't forget that one. But does this pass the vertical line test? Yeah. Yes. So if this question was on your test and you said, yes, it's a function because it passes the vertical line test, that's great as long as you do this part. You have to sketch it and show me the vertical line test, please. So then I want you to give me an example of a list of ordered pairs that is not a function. So, that's my question. Which one is it? Is it the x's or the y's? Girls are x's. Okay, so the x's cannot repeat, right? The x's can't be paired more than once. So an example of something that's not a function. Let's go like 3, 4, 5, 2, and give me an example of a third point that would create this to be not a function.
3.
Yep, anything.
7.
What?
7.
Wow, 7, get crazy. All right, so why is this not a function? Explain in detail. Because x equals 3 is paired twice. That would be a totally adequate answer. Does it matter if the y's are paired twice? No, it's just the x's. Very good. All right. Again, this is a repeating thing. Or is this a repeating thing? Yeah, it is. A minus 4 is what you're plugging into this function. So be careful, guys. This one has a lot of distribution. So if you're putting a minus 4 into this quantity being squared, you're going to need to square this first. But remember, a minus 4 squared is it's a foiling question, right? A minus 4 times another a minus 4. So this is really, what, a squared minus 8a plus 16. But also, please don't forget, there's still a negative 3 in front. So then you're going to distribute your negative 3, and then you're going to collect your like terms at the end of it. So I'll let you finish up that question. A little note. Need to finish this. Now, this next question, I don't know why this gave people trouble last year, because it's not meant to be really difficult. You're plugging in a -6n into that function. So I always start by writing what I call the skeleton of the function. And then I just place the input into the skeleton. I think what happened last year was kids were forgetting their order of operations. Inside the parentheses first, and then exponents. So there's nothing to do in the parentheses, but you need to square this term before you multiply by -3. These are the same exact questions, we just have a little different input. So when you square -6n, that becomes a 36n squared. But he's still being multiplied by -3, and then you still need to add 1 at the end. Is that -108n squared and then plus 1? So, yeah, it's been a long time since I gave that question on a test, but I think the issue was they would try to multiply the -3 with the -6 and then do some weird things, so we know that's not right. Follow your order of operations, children. All right, this is still an old attempt. This is your second attempt at domain, range, and symmetry. So this function, I know it's very hard to see on your paper, just do the best you can, but it has a starting point here, and then it does like a weird little squiggly thing, and then there's like an arrow here. So when I ask you for domain, remember domain is the interval for your x's from least to greatest, so left to right. The x's start right here. Let's pretend that is exactly at -3. Now why am I using a bracket? Because there is a point. Yeah. The only time you would use a parenthesis is if you're looking at an infinity, or if there's an asymptote, or if there's a hole. And we don't have any of those things right there. And then it goes from -3 to positive infinity, all the way to the right. So parenthesis on infinity. The range, remember, has to be least to greatest. So how low does this function travel in the y direction? -infinity. And then it stops at what y value, approximately? Yeah, I'm going to go with 4. Bracket or parenthesis on the 4? Bracket, because it ends at a point. Some of you were getting your intervals backwards last time. That is a concept error. Some of you were using parenthesis when you should use a bracket, so be careful there. We can come back to this if we want some extra practice on increasing and decreasing in a minute. Here's some extra practice. We'll come back if we need it. Okay, old topic still. When is this discontinuous? So remember, for a rational function, the only place it's discontinuous is when your denominator comes out to 0. Because we know we can't divide by 0. So previously, the question on your test, this was really easy. It was like a linear piece, but this is a quadratic piece. So choose your favorite method of solving a quadratic. I'm going to go with factoring. And that factors pretty nicely, doesn't it? X minus 1 times x minus 6. So when you solve your factors, it turns out x equals 6 would produce a discontinuity, and x equals 1 would produce a discontinuity. So it says, for what values is it discontinuous? Both of those values right there. I think the way this shows up on your test tomorrow, I think it's a multiple choice question. So you choose which one works. Or doesn't work in that case. Because if you were to plug in x equals 6 into this denominator, after you do the calculation, it would come out to a 0. And it would be like something divided by 0, which we know we can't have. All right. Oh, the stinking even odd thing. Okay, so when you're looking at a graph, how do you know if your function is, let's do the easier one. How do you know if it's even? What kind of symmetry does it have if your function is even? That's right, class. It's y-axis symmetry. So on the last test, I had to do this to a lot of people's papers. I would highlight the y-axis. Now look at that parabola, guys. Is it splitting straight through the middle on the y-axis? No, it is not. So this does not have even symmetry. So this one is actually neither. Because the other type of symmetry, that's hidden here, but odd functions have symmetry of the origin. So like for instance, I don't know what ordered pair this is because I can't see that small of numbers, but these are reflections across the origin. Positive, positive, negative, negative. These guys are reflections of each other across the origin. Negative, positive, positive, negative. They just switch signs, basically, is what's happening. The way I visualize it is I think about folding my paper along the x-axis and the y-axis, and you end up with the same mapping. That's how the symmetry works. So this one does have symmetry of the origin, which means this one is odd. On your previous exam, we had some questions about doing the algebraic testing. If you wanted to know about the algebraic testing for odd symmetry, when you plug in a negative x, you get the opposite function. For even symmetry, when you plug in a negative x, you just get your regular function back. So I don't remember if that kind of question shows up on your test tomorrow, but it could show up in the future, and it does show up on like your final exam and stuff, so it's good to talk about. Can we talk about this one real quick? It's not on your paper anywhere. Anyone have any thoughts about whether this is even, odd, or neither? It's neither. A lot of kids think it's even because they think about the origin and something happens at the origin, but this peak does not match up with a peak over here, so it is not even, clearly not odd, so that would be a neither. What about this one here? That is definitely even. There you go. Alright. So here, I believe this is the first time we have tested this. So on your calculator, get that function typed into y equals, and we all got to practice finding all these things. So you're going to need to find zeros. It'll be listed out for you on the test, but you have a max, a relative max, you have a relative min, you have zeros. Increasing and decreasing intervals. The other thing we're going to need to find is the inflection point. And then concave up, concave down, oh my goodness. And then you know what? The other thing we need to talk about is end behavior. At least that one's easy for us at this point. All right. I'm going to go through finding a few of these things on our calculator just in case a few of you get stuck on what to do, but you do need to get a good picture. So if you're in the standard viewing window, you're not going to be able to see either the max or the min. So you need to extend your Y window. And that minimum is pretty far down. So I'm going to go to like negative 50. I think that's far enough. And then I'm going to go to 20 for the Y max. That works. All right. So you need to find that 0, and that 0. I don't think it says here where to round, but it does very specifically say on your test to go to the nearest 100th place. So I'm looking for 2 decimal points. I'm going to find one of the X-Intercepts, and then I'm going to kind of, through the art of I already keyed it, I'm just going to tell you the other ones. So for X-Intercepts, who can remind me which command I choose? The 0, yes. And then you got to follow the instructions. They want your cursor to the left, so I'm going to find this one first. I'm going to hop over here to like negative 8. And then something to the right, so I'm going to go to negative 4. And my intercept is in between those two lines, so I'm going to hit enter one last time. And I'm going to write down negative 5.60 because I'm rounding. You can write them as ordered pairs if you'd like. If you just wrote down negative 5.60, that's fine. The other X-intercepts are negative 0.51 and 2.10, I believe. So those are all found the same way, left bound, right bound, enter. So back to our calculator, let's go find our maximum and our minimum, those relative bumps. So be careful which command you're choosing. Like if I go to find this one first, what am I finding? That's a minimum, yeah. So calc menu, I'm going to find a minimum, so choose that. My cursor's already to the left of it, so cool, hit enter. And then I'm going to hop to the right of it, I'm going to go to like negative 2. And the minimum is in between those two lines, so I'm good to go. Hit enter. And this time I need you to write down the entire ordered pair, negative 3.59, negative 35.18. And put it under the minimum, please. So, through the art of I already keyed this, that maximum bump is at 0.93. 11.04. I hope. Now, for this next question, the increasing decreasing interval, we did this in our notes and our homework, and I would like to continue this tradition because I think it's really going to help you on your test. I'm going to grab a highlighter or a pen or something, and I'm going to mark up the X values of my minimum and maximum, because when I go to answer these next few questions, those are the numbers I need to use. Those plus any infinity that I might encounter. So I'm going to go back to my calculator. When I'm asking for an increasing interval versus a decreasing interval, the first time the function's traveling this roller coaster, this is a decreasing interval. And then it changes to an increasing interval. And then at that peak, it switches back to a decreasing interval. So, answering me very carefully, when is your roller coaster increasing? When does it start its increasing behavior? At negative 3.59. And when does it stop? 0.93. Okay. And then the other parts is when it's decreasing. So from left to right, it's decreasing starting at negative infinity. And then it stops decreasing at negative 3.59. Make sure you're using parentheses here. And then also it's decreasing from 0.93 and then forever. Okay. Notice the only numbers we used were those ones that we just marked with highlighter. Okay. So the next couple questions. These all kind of go together. I'm going to ask you to estimate the inflection point. I'm going to go back to my calculator because I kind of like this emulator because I can draw on it. That's nice. I'm going to erase all the other markings I have. And remember, guys, on your homework, I suggested when you did these homework questions to kind of sketch yourself like 2 different graphs because you do so much marking on them sometimes that it's hard to see. The inflection point occurs right in the middle of your 2 peaks. So your inflection point is like somewhere right here. Now, technically, I would accept literally an estimate. So, like, if you think you can eyeball where that's located, that's probably okay. But it's not that hard to find the middle of 2 numbers, guys. Don't you just add them up and divide by 2? So, this number here, remember, was negative 3.59. That's how far over it is. And this number here was 0.93. So, to find the x value of your inflection point, just find the middle of that. So, negative 3.59 plus 0.93. And then find the middle. And that's going to be a really good estimate for your inflection point, at least the x value of it. And I think I got, what'd I get? Negative 1.33? Someone confirm that number for me? Okay. Now, I think on your test, it writes it as an ordered pair. There's a really easy way for you guys to find the y value of that ordered pair. Just go to your calculator, because you already have your function typed in. And if you pull up the trace, which pulls up the cursor, and then type negative 1.33, that's a way to just quickly evaluate a number without having to go to your table. So apparently that's at negative 12.02. Jot that down. I didn't make you do that part on your homework, but I think it's written that way. Alright, so again, grab that trusty highlighter, because the only number you're allowed to use here is that x value of the inflection point. You can't use the y value. It has nothing to do with intervals. So when is this concave up versus when is this concave down? Alright, you know what? Back to my calculator here. I like this picture. Oh, not that. There's only one inflection point, which means half of your graph is a smiley face and half of your graph is a frowny face. This first half, is it smiley face or frowny face? Smiley face. So this would be concave up. And then at the inflection point, it switches to concave down, a frowny face. So your job now is just to write that as an interval. It's concave up from negative infinity until when does it switch? When does it inflect? Negative 1.33. And then it's frowny face after that, so negative 1.33 to infinity. I think if you guys highlight the x's on all those ordered pairs, you'll have a lot better luck with the intervals. And it's not that you don't know what you're doing, but when kids have all these numbers sitting on their paper and they're asked to come up with an interval, it's a lot to look at. It's really easy to pull the wrong number. So take my advice or don't, whatever. Now you guys do have to know the end behavior template. So it looks a little like this. Function approaches something as x goes to the left, and your function goes to somewhere as x goes to the right. So I don't have the picture in front of me anymore, but it looks something like this, didn't it? So on the left side, which is x goes to negative infinity, what is your function doing? Where is it approaching? Up, up, up to infinity. And then on the right side, it's going down, down, down to negative infinity. Yes, you need to know the end behavior template from memory. All right, I'm sure there's more examples of this coming up on future slides. We can come back to that if we have time. Okie dokie, talk about transformations. Describe the transformations from the parent function to this new function. In order, please. Oh my goodness, thank you, Mrs. Hoffbauer. Okay, so the order really does matter, guys. There's a question coming up where it really matters because you're going to create the function. But if you're ever in a jam, just start from the left and work your way to the right, and you'll probably be fine. So what would you call this 3? Give me some words that we associate with throwing a 3 in front of a function. A vertical stretch of 3. Very good. And then, what sort of transformation would be associated with having an x plus 5 in the body? That would be a left 5. Very good. And then finally, you have a negative 1 outside of the body, which means it's down 1. Very good. All right. Similarly here, start on the left, work your way to the right. What happens when you throw a negative in front of the body of the function like that? Yes. So that's been reflected over specifically where? Yep. So reflected over the x-axis. If you call that a vertical reflection, I'll accept that. So reflected over the x-axis. And then when you have x minus 2 in the body, what does that mean? Right 2. Very good. And then plus 7 outside of the body means up 7. Very good. Okay, this one I'm a little worried about. I'm specifically giving you order of transformations. You cannot mess with the order. So starting at number 1, working your way down the list. You'll see what I mean in a minute. So this function starts off with the square root of x, but then I'm going to vertically shrink it by a factor of 1/2. So what shows a vertical contraction or vertical shrink? Is that in or out? Out of the function. So you throw a 1/2 in front of the function. That's a vertical shrink of 1/2. And then you have to apply a left 3 shift. So that would look like an x plus 3 right here in the body. And then you have to show me an up 5 shift. So out of the body, a plus 5. And this is where everyone's going to get a little confused. Now I need you reflected over the x-axis. So at the very end, if you do a reflection, what you have to do is this. Do you see how order matters all of a sudden? If you reflected at the end of your transformations, what else could you do to this problem, by the way? Because I'm okay with this being your answer. But could we distribute the negative? So I would also accept negatives 1/2 square root of x plus 3. But then what happens to this up 5 shift? It's really a down 5 shift, yeah. So either one of these are acceptable. If you're worried about it, just don't mess with it. That would be my suggestion. So in order, you apply those transformations. So if they put anything like outside of the function at the very end of your orders, you gotta think about that as being distributed to everybody. So either use parentheses or go ahead and distribute it yourself. All right, this is on your notes or on your paper, and it's gonna be a matching question. So I know we've done a few warm-ups with these, and there's some on your homework. However, these are kind of annoying to draw. So let me kind of go through what you're supposed to do. Can you guys describe for me real quick what happens when you throw a 2 in front of your function like this? It's a vertical stretch of 2. So all of your y values are going to be amplified by 2 or multiplied by 2. Okay, old lady eyes. Let's see if I can do this. Well, these aren't too bad, because anything that's on the axes is not going to move. So what is that at -3? So -3, 0 is still going to be at -3, 0, because when you multiply a y value of 0 by 2, you're still at 0. Same thing here with +3. But this ordered pair, which, oh my gosh, is that at 2, 3, the original? And then this ordered pair is at 0, 3. Both of those y values are going to get multiplied by 2. So instead of being at 2, 3, he's now at 2, 6. Put it all the way to the top. And then instead of being at 0, 3, he's at 0, 6. Now, I have really great news for you. You are not going to have to hand draw the transformations on this weird function, I think, this time. I think this time it's a matching question only. So, yay. This one, oh boy. If you throw a negative in front of your function, and then you have an x plus 3. And then now everyone's all paranoid about order. This is a vertical reflection, and this is a horizontal shift. So it doesn't matter which order you do them in, because they're not competing against each other. So we know we have to reflect over the x-axis, and then we also have to move left 3. Oh boy, here we go. So like this ordered pair here, which this guy is at -3, 0. This one's at 3, 0. So if you take -3, 0 and you reflect it over the x-axis, that's really boring because it's still going to be at -3, 0. But then if you shift it left 3 units, now it's over here at -6, 0. And then this guy, 3, 0, if you reflect it over the x-axis, that's pretty boring. It doesn't go anywhere. But then you're going to shift left 3 units. You're going to be at 0, 0. Okay, these top ones get a little more exciting. So if I take the ordered pair 0, 3, and I reflect it over the x-axis, I'm down here at 0, -3. And then I'm going to move left 3 units. 1, 2, 3. And then same thing with 2, 3. I'm going to reflect it over the x-axis. And I'm going to move left 1, 2, 3. Oh my goodness. These are so horrible to draw by hand. I'm sorry. Beautiful. All right, this is the next one. When you throw a 1/2 in front of a function, that means you're going to vertically shrink by half. For the sake of time, I'm going to kind of skip doing that one, but basically you take those top y values and you pull them down by a factor of half. So instead of being at 0, 3, that one's going to now be at 0, 1.5. Instead of being at 2, 3, it's going to be at 2, 1.5. This one I'm interested in, though. Do you remember what it's called when you throw a 3 into the function like that? It's a horizontal. This one's actually a shrink. Very good. So you're going to horizontally compress or contract or shrink, whatever word you want to use, by a factor of 3. So it changes the x value. So like for instance, this -3, 0 is going to shrink by a factor of 3. So divided by 3, it's now going to be at -1, 0. This guy's 3, 0 is going to shrink by a factor of 3. It's going to be at +1, 0. And then these are a little confusing. This one doesn't move, because 0, 3, if you take 0 and you shrink it by a factor of 3, it's still going to be at 0. But this one's a little hard to get to, guys. If you take 2 and you shrink it by a factor of 3, so like divide by 3, it's going to be at 2/3. Good luck. All right, so like there's a point like right here. Notice, oh man, I missed. Notice we did not mess with how high or low the function went. All we did was we horizontally contracted it. So I want to reiterate, you guys are not going to have to draw that one. You're going to be matching them up. Good luck. That was not a lot of fun. And frankly, guys, I don't want to grade that. Like, I can't draw it. No, you're matching it. You'll be fine. Now, be better than last year. Last year, they had a tough time with that one, so that made me sad. All right. We have some more examples we can get to later if we have time. Looks like we might have a little time. Okay, I can identify the parent function, and then I can create the functions. This is what we did yesterday. So first, from memory, can you identify for me what function we're looking at? There's an arrow down here. It's the square root function. I heard someone whisper. Thank you. So the transformational form for the square root function is y equals a times the square root of x minus h plus k. So it's not called a vertex, but the starting point of your square root function is where the h and k have been shifted. So, oh my gosh, old lady eyes, here we go. I think that's at -6, 1. Can your young people eyes confirm that? Oh, good, okay. And then there's a couple of ordered pairs that have been strategically plotted for you. I'm going to go with this one here. I think on the test, if I didn't plot and put a point there, don't use anything other than what I've plotted for you. So we can assume that's a nice number. I'm going to go with, I think that's -5, -2. So this blue part, whoops, this blue part here is HK. And this other red point we're going to use as our XY. And we're going to plug in all those clues in order to find A. Now tell me something you know about A before I actually do any calculating. Can you tell it's been reflected? So your A is going to be negative. The other thing I can tell is that, to me it looks like it's been vertically stretched, but I guess we'll find out. All of this math works out by itself. You guys don't have to think about it. All right, the y value is -2 for that random ordered pair. The x value associated with that was -5. The h was -6, so you're going to do one of these things. And then the k value was a 1. So solving for A, you're going to start by subtracting the 1 over. You get -3 equals A. And then this is 1, square root of 1 is just a 1. That's kind of boring. Normally I'd say divide this number over. Super boring though. A is just -3. Hey, that's exactly what we thought. It's negative, so it's reflected, and it's been stretched. So your new function is -3 square root x minus h will be x plus 6, and then plus k. So just so we're all clear, you're responsible to know the transformational formulas. It's not rocket science though, guys. It's the same formula every single time, just the body changes. So if it's a square root, that's the body. If it's parabolas, that's the body. If it's cubic, that's the body. You got this. Oh, piecewise. Here we go. This is another part of the test I really don't like grading. I think like my inner poor drawer empathizes with everyone when it comes to piecewise. So the first couple questions, you don't have to draw, you just have to evaluate. And your piecewise function has 3 parts. This top part here, this parabola component, is only for x's that are less than -2. This middle part, this constant function, is for x's between -2 and 3. And then this bottom part is an absolute value component, but it's only for x's that are bigger than 3. So when it says evaluate your function when x equals -5, should you be using the top function, the middle function, or the bottom function? That goes with the top function because x's are less than -2. So going through your top function piece and evaluating -2 and then -5 plus 4 quantity squared, I think that comes out to -2. So what if my x value is exactly -2? Top, middle, or bottom? Middle this time. So this is kind of weird because your middle function is constant. So no matter what you're trying to quote plug in, it's always going to come out to a 3. And then what if I'm plugging in x equals 4? That's that top function, isn't it? Or sorry, bottom function, excuse me. So -3 absolute value, plug in a 4 minus 5 plus 9. So remember when you evaluate absolute value, you evaluate the inside. That's a -1, but it's the absolute value of -1 times -3 plus 9. So absolute value of -1 is +1. -3 times 1 is -3 plus 9 is 6. All right. Weird. Let's graph. All right, same function. For me, I like to put boundary lines wherever I have a domain switch. So -2 and 3 are going to be my places where it switches. I'm going to go ahead and mark that up. Then, some pieces of this are going to be very easy to graph, and some pieces are going to take a little thinking and a little evaluating. What I want you guys to remember is you have a graphing calculator at your fingertips. So if you're ever like, oh snap, I can't figure out what this looks like, graph the function in y equals, go pull up some points from your table, just make sure you're only plotting points that work for your domain. So when x is less than -2, I'm supposed to graph this parabola. I'm going to go ahead and plug in a -2, but I notice it doesn't have an equal to sign, so when I go to plot that point, I'm going to need to plot an open circle because it doesn't actually exist there. So plugging in a -2 to this function, let's see, -2 plus 4 is 2, 2 squared is 4, 4 times -2 is -8. So at -2, -8, I need to draw an open circle. And you have to have stuff going on your boundary line, whether it's an open or closed circle is dependent on the sign. Now, I'm not going to just be able to plot one more point and then call it a day. This is a parabola. This particular parabola has been shifted left 4 units, and then it's been reflected and stretched. So you already know a lot about this parabola. You know his vertex is right here. You could probably figure out another ordered pair pretty quickly, guys, whether it's through your calculator or using the old noggin. I don't really care. I'd like an ordered pair off to this side, so I'm going to go ahead and plug in something like -6. So if I plug in a -6 right here, -6 plus 4 is -2. -2 squared is 4. -2 times 4 is -8 again. There's that symmetry we like to see on a parabola. Aw, snap, I missed. Okay. That was supposed to be a parabola. Notice, guys, it's not the whole parabola, because after x equals -2, it cuts off. But moral of the story here is if you're not graphing something that's linear, you need to graph quite a few points in order to get a real accurate description and a real good picture. Oh man, it's like my birthday when they give me a constant function. X equals 3, or sorry, excuse me, y equals 3 is just a horizontal line at 3. The only thing you guys got to determine is whether it's got open or closed circles. So it's got a closed circle on -2, and then it's got an open circle over here. Cool. And then this last piece, this is an absolute value function. I'm going to go ahead and figure out the boundary line point, even though it doesn't really exist. So I'm going to make a note that I got to put an open circle. But open circle, when you plug in x equals 3, let's see. 3 minus 5 is -2. Absolute value of -2 is 2. -3 times 2 is -6. -6 plus 9 is 3. So at 3, 3, I'm supposed to graph an open circle. Uh-oh. Now, they overlapped. But did that point ever close up? No. So there is a hole at x equals -3. Keep that in mind for our next question. If this had an equal to bar underneath it, we would have filled that point in, and they would have overlapped the hole, and there would be no hole anymore, okay? Filled in points overlap holes. Anywho, this is an absolute value graph that's been shifted right 5 and up 9. So I'm just going to go ahead and quickly plot my vertex. And absolute values are pretty easy to graph because that A value is the slope of the branch because they are secretly linear. So if you travel down 3, right 1, or left 1, and down 3, right 1, you can see enough points where you can graph this absolute value. Now remember, guys, these are V-shaped. Oh man, I killed that. Look at that. Alright, so my next question for you is about discontinuities. Do you see any places where there's a... Now that I see a picture, I totally see discontinuities, guys. Do you see them? At x equals what? Where's the first gigantic discontinuity? At -2. There's a huge jump, which means a discontinuity. And we talked about this, guys, but did this hole ever get filled in? No, so there's also a discontinuity at x equals 3. If that hole gets filled in, it is no longer discontinuous. Got it? And then real quick, this guy. There are arrows on the ends here, guys. There are arrows there. Is that the one you have? That is? Okay, good. So when I go to write my piecewise function, there's two pieces. The first one is for x's that are less than -1. And then the next piece for x's between... Oh, I screwed up. I thought there was an arrow on my key. I gotta fix that. X is between -1 and 3. But I noticed that there's an open circle on 3, so I didn't close it off there. This is a constant function at... I can't read that. Is that -4? This guy? And then this piece is a line. So he's got a y-intercept at 3. -3, excuse me. And if I count carefully, I think the slope was -1. So I'm going to write -x minus 3, and I apologize, because if you looked at my key, I had a boo-boo right there, because I thought there was an arrow. Ta-da! Alright, looks like we don't have time to go over any extras, guys, sorry. There's some matching things on the back of that packet. You can go back through the video and kind of pause the video on all the slides and redo those extra questions if you want. Maybe Hofbauer's better than me, and she got a lot further and did some extras. Alright, good luck!